Welcome to continuation of our discussions on topics in abstract algebra, where we're going to continue with our discussions on the Klein's group. So I welcome to illustration. Because I welcome to continuation of our discussions on Klein's group. You know, we identified the Klein's group as being B4, which we said was given rise to E, U, V, and W, where we identify also that U squared, same as V squared, same as W squared, and was the same as our identity permutation, okay, which we also can also write as E. So what we are going to do is to now try to identify subgroups of these four, the Klein groups. The first one, let me call it C1, which is E and U. Second one, C2, is E and V. Third one is C3, which will give us E and W. Now, this is so because this group is actually E, U squared, which was actually E. Okay, so it was actually the group generated by U. Okay, and this group is also E, V. Remember our V square was also E. Okay, so that means this group is a cyclic group generated by V. Okay. V. Okay. This group is also can be written as E W. W square was also E. So that means this group is generated by W. So that means this implies that the CI, where I runs from 1, 2, and 3, actually form cyclic groups. Let me call them subgroup because they are subgroup. Okay. Subgroups of V4. Okay, this implies that C1 is a subgroup, is cyclic. And why do we say it's cyclic? Because it's generated by a single element U. Okay? You can see U square is E, so it's like just E and U. Okay, V is also cyclic. W is also cyclic. So they are also cyclic. They are also, these groups are also, or let me call it subgroups, are also therefore normal. Okay, normal in B4. You remember our theorem that cyclic subgroups are actually normal in subgroups. This can be verified. We can verify it. We can use computations, our usual computations to verify. What all you need to do is to pick an element in V4 like U and try to show that U into any one of them. Maybe EU, okay, will be the same as what? EU times U, that will be the same. For example, E times, this is going to be UE, U times U, okay, and this is going to be EU, EU, UU. Of course, we know by definition this is simply U because this is identity element, and this is by definition is U squared, which we know is E. Okay, so this one is actually just E under what? U. What of this one? This one By definition, we know it's just u, e times u is u, u is also u squared, and we know u square is e by the property of u. So this also boils down to eu. So that means they are the same. So that the left coset and right coset are the same, meaning that these groups are normal. You can do it for other subgroups also. So I welcome to next presentation.